Every single day, we walk into houses, offices, and shopping malls without a second thought. We trust that the floor won't give way and the roof won't collapse. But have you ever stopped to wonder exactly how a building manages to carry all that weight safely into the ground? Good morning. Today, I want to teach you about the invisible anatomy of a building. We are going to look behind the drywall and beneath the floor tiles to understand these three critical components of structural design: the ultimate load, the lateral reinforcement, and the foundation pressure. By the end of this presentation, you will look at the buildings around you in a completely different way. Let's start from the top and work our way down. In structural engineering, every piece of furniture, every person, and the weight of the concrete itself is calculated and factored into what we call the ultimate load, or PU. Imagine a standard four-story building. All the weight from the upper floors has to travel down through the columns. As an example, a single ground floor column in this type of building might be subjected to a PU of exactly 550 kilonewtons. To put that into perspective, 550 is roughly equivalent to balancing the weight of over 13 mid-sized cars on a single concrete pillar. To survive that massive downward force without crushing, the column needs more than just concrete. This brings us to our second point: reinforcement. Concrete is incredibly strong when you compress it, but it is weak when it stretches or bends. Because of this, we embed thick vertical steel bars inside the concrete. However, under 550 kN of pressure, those vertical steel bars want to buckle and bow outward. To stop this, we wrap the main vertical bars with smaller steel loops called lateral ties. A common and highly effective standard for this is using 10 mm lateral ties spaced carefully along the height of the column. These 10 mm bars essentially squeeze the vertical rebars together, confining the concrete core and ensuring the column doesn't bulge or snap under the immense pressure. And finally, that load has to go into the earth. The column sits on a wide concrete pad buried underground called a footing. Designing this footing is arguably the most critical part of the process. Because the soil can only handle so much pressure before it shifts or sinks, a common misconception when sizing a footing is to calculate it using the maximum soil pressure, or Qmax. However, to ensure absolute accuracy and safety, we must prioritize the effective soil pressure, or Q effective. By using this to determine the size of the footing, we account for the weight of the soil that was excavated and the actual net pressure applied by the building. It ensures our foundation is perfectly sized, neither dangerously small nor wastefully large. And to wrap up, a building's survival relies on a perfectly calculated chain of events. It requires anticipating the ultimate load, like our example, securing the structure with 10 mm lateral ties, and carefully dispersing that weight into the earth using the effective soil pressure. The next time you walk into a multi-story building, I hope you take a moment to appreciate the incredible invisible math working silently around you to keep you safe. Thank you for your time and attention today.